Hi, fellow geochemists and geochemistry enthusiasts. Welcome to Geochemist Tea, the only podcast for people who really love geochemistry with a side of tea. Our mission is to inspire and to shed light on the topics not fancy enough to talk about at a conference, but really important to delve into. I'm your host, Sam Scher, and this week we are talking with Andrew Summers about field portable geochemistry, specifically focusing on LIBS and how the correct applications of these tools is changing the landscape of geochemistry in our industry. To freshen up on the capabilities of LIBS, check out Harmon et al. 2019 LIBS, an emerging tool for mineral exploration. Andrew Summers is the Global Business Director for Geochemistry at SciAps. Andrew, welcome to Geochemistry.
Thank you, Sam. Thanks for the opportunity to speak on your podcast.
Honestly, I'm just excited that you're here. So Andrew, you have a long history of working on the business side of mining. However, you also have quite a strong background in geochemistry and technology. Can you talk to our listeners about the evolution of your career and draw towards promoting field-based geochemistry?
Sure, Sam. So, I guess I've had a winding road to this point. The last few years has been essentially doing a similar job in a lot of different companies that have all been an evolution of the initial company I worked with being bought by other companies until the move to SciAps a few years ago. So I did start off as a geologist, working with Rio Tinto Exploration in Darwin, and I guess was one of the geologists that in the ups and downs of our industry ended up changing or going to change my direction. And I went back to uni and did my master's and was intending to go back to work in more of an environmental science field, and came across a job interview for an environmental consultancy that also happened to work in the very early days with the Niton handheld XRF. And so they asked me, with the background that I had, if I'd be interested in working more with the field portable analytical products. I had never really heard of those products before. This is like 2004, and things were just really kicking off. And I had a look at it and thought about it, said I'd get back to them the next day, and the rest is history. I started working somewhat by chance in field portable XRFs. I thought they looked really cool, and have subsequently worked through the evolution of that product, the direction of that company. JBS, that was the company, was the Australian Niton rep, was mostly contaminated land management and using portable XRFs for lead paint as well. And so they were involved in a project with Perillia, acquiring the Broken Hill properties from Pasminco in that period. And certainly the exploration manager and the MD at the time saw the advantages in being able to map lead in soil in a contaminated land management environment, and really wanted to push that out into a mineral exploration application. So we're involved with some people that you would know already in the industry, such as Todd Houlihan. He was moving to work with Niton at the time. This is before Thermo bought them in Europe. And essentially I stepped into a gap that he left in JBS. So it was a wild ride, obviously, through the early 2000s with the mineral exploration boom there. We had a lot of success with the portable XRF. And, subsequently the company, JBS, was acquired by Innovex, another field portable XRF manufacturer at the time. So I took on the managing director role for Australia for Innovex and continued to support and work with product development and the global mining team to promote and further the products and their application into mineral exploration, mining, mineral processing, and contaminated land cleanup at post-mining activity. So subsequent to that, I guess we've worked through Olympus acquiring Innovex. Now they're Evident. and worked with those guys. And then obviously the team that started Innovex started SciAps around 10 years ago now, and I joined them at very early days, primarily working with the LIBS product that we talk about in the paper, and also we'll be discussing today, but also in portable XRF, and we have worked, with Raman. I've worked with near-infrared products as well. So a range of different field portable analytical tools, both for geochemical and mineralogical analysis.
Yeah, I think that's so interesting, and I guess usually I ask at this point, do you have any tips or advice to give listeners that want to break into geochemistry and mineral exploration? But do you have any advice for people that have a similar background to the two of us, where we've worked with a lot of geochemistry, we've worked also geology, mining, exploration, that kind of want to do a pivot such as you did, into working in the business side, but then also really working into the technology side of this?
Yeah, certainly. I mean, the geology space, I guess, at the moment is pretty hot. So for technology companies, finding candidates that are suitable and willing is probably the hardest thing. So within the group, I guess, of people that have had exposure and are practitioners with field portable technologies, certainly different things happen in your life. Sometimes you want to take a different road. I think there's currently a lot of opportunities in companies that are manufacturing portable XRF and other portable techniques, analytical products, to make that transition if they're interested. When I guess it comes down to the willingness of the person and the interest of that person in order to really want to make that move. So, I think we do have some experience with geologists not being probably ideal for sales in particular. Sometimes we found that it's easier to train a salesperson to do rudimentary kind of industry interface than it is to train a geologist to sell. But I think there's definitely people out there that have a natural flair for interfacing with people, with client management. Certainly in product development, these are key areas where people that are coming from a geoscience perspective can transition across. I think there's a lot more roles as well on the other side now. So certainly a lot of the mineral exploration mining companies now have key technology and innovation positions. And so, there's a lot of cross-pollination, I guess, and this is a really important thing, I think, in terms of developing products that are fit for purpose for the industry that we work in, is having a genuine interface between the client side and the manufacturer side, because manufacturers often find it very difficult to create the impetus to build a product that's specific to a need, and certainly the more feedback and the more willingness we have for companies to work collaboratively on both ways to help support the demand for those products and to help specify exactly what they're chasing is really important. So having people from the geosciences that are actually right into this field portable technology space, or even core scanning systems, all these types of things that are evolving in that ecosystem at the moment, the more knowledge that we've got from a manufacturer perspective about what the industry really needs and wants, the more successful we're going to be, and the more likely we're going to be to invest in building products. I mean, this is an issue I think that the industry faces, is the METS interface, and certainly the chicken and egg problem of getting gear that really hits the nail on the head for a lot of users. So the other side, I guess, in terms of field-based technologies and even just geochemistry and Minex, is people have to be genuinely passionate about what they're doing and interested in making things happen that aren't possible at the moment with technology. So certainly there's a lot of interesting things happening at the moment in terms of field-based sensors or in situ sensors, and being able to use multiple data streams to form better information around geological materials. And so, we're seeing this explosion at the moment in data science as well, which I know is, a term that's overused in some conversations, but certainly it's relevant to this. And I think that people that want to move forward in this technology space need to have some awareness and capability in that space, whether they're a geologist or a technologist, in order to make this stuff all really sing.
I love it. You hit on so many different points, and I'm just thinking about all the people that I've talked to the past year. I'm just hearing Mike Whitbread over here. I'm hearing Simon over here, Pim over here, talking with Putra the other day. That was an awesome introduction, Andrew. But now let's see if your tea is as good. So please, dish.
Well, I think I want to sort of follow on a little bit from that initial segue into this section around the METS interface, but also around the ideas of supply chain disruption affecting access to technology. I think it really fits in like a hand in a glove. The supply demand curve here, that the more successful uptake is with different technologies, generally you'd expect that the companies that are manufacturing these things would be continually innovating and improving what they're offering, making sure that they're future-proofing their ability to offer products. And at the moment, it seems that this global supply chain disruption, as well as affecting access to your brand new Land Cruiser, is also impacting severely access to your favorite XRF or to your handheld near-infrared system, or whatever it may be. There's been a swathe of different products that have hit supply constraints around access and ability, just at a time when the industry is really crying out for more of it and in an upswing in activity. So I think other areas as well here, that the wait times on getting equipment, or even equipment just being discontinued, that is really kind of a pertinent point. And I think that the industry can wring their hands about this to some extent. They have to also understand, the mineral industry, that that these manufacturers are often building this equipment for a multitude of market segments. And I know it comes as a surprise to some people when you talk to them that the mineral exploration in particular is probably quite a small segment. Even with portable XRF, you might be looking at 20% maybe of the total sales going into mineral exploration per se for portable XRF. So I mean, we are seeing that they've been used de rigueur these days, but still, they're not used by everyone. They're not well understood and used well by everyone. And the manufacturers kind of phase in and out of their ability to deliver quality, fit-for-purpose product that actually satisfies the requirement of the user group that we're talking about today. So, this is a key thing, I think, that companies on our side need to have that commitment to innovate. They need to have the ability to be nimble and to deal with these supply chain disruptions. They need to be able to predict when there's going to be surges in demand, as there is at the moment, and build towards it. And I don't know if that's happening. And like I said, it's a chicken and egg issue. It's a push-pull problem that we see that these companies, especially as they get bought up by bigger and bigger and bigger companies, the importance of those specific analytical tools that we rely on in the field as geologists, geochemists, mineralogists, they sort of fall into insignificance when they're a line item on the bottom of a catalog, And some of these companies that buy these companies that start off as quite innovative and interesting companies and that are committed companies to the mineral industry, often that becomes diluted over time. So I think that it does require constant nurturing by industry to maintain the ability for these products to actually be available. So I don't know if that's juicy enough or gossipy enough, but I think it's a key point in this space at the moment.
I really like that, because I feel like there's probably 5 examples right off the top of my head that I'm thinking about. I'm thinking about one, the Tear Spec Halo that's going out of production, and it's going out of production, from my understanding, because there's a piece that's only built by one guy, and that guy has retired. And it's like, did you guys not
see
plan
that coming?
for this?
Yeah.
Exactly. Like this seems ridiculous in this day and age. Anyway, so that's one of them. And the other one I can think of, because now we get a little bit into the gossip, is when Speckham that was acquired by Konica Minolta. And I just think about that. For anybody who doesn't know, Speckham provides hyperspectral instrumentation to the mining industry, but also to many other parts of different industries. And we are a very small piece of that pie. And now being bought by such a large company, it's like, where's our future? being able to use this piece of equipment. And I think you're very right in the sense that everything in mining is just always, oh, it's too expensive, it's too expensive, it's too expensive. And when we're ready to commit, then it's just like these pieces that we need aren't there. And it's because we haven't done that whole nurturing of the technology and keeping up with it and making our projects better the whole time, and not until, you know, we get somebody into, as you talk about, into one of these innovation groups that's just like, okay, it's time to really get this rolling, this mineralogy rolling. Okay, let's, you know, let's invest in this and we'll plan it this way. And they come up with a really great plan, but then all of a sudden you can't even buy the instrumentation that you need because that one guy has retired. So
yeah,
no,
and
I think this is a
it comes down
great.
to people taking their eye off the ball because, as I said, the powers that be become less focused on that level of detail. You know what I mean? That who knows why Konica Minolta bought those guys for a part of their IP, to fill a gap in their product offering. There was obviously a justification, but it probably didn't relate to fitting it onto a core scanning system to do high resolution hyperspectral work. You know, like, I mean, that's the hard truth. And so, you know, I mean, there has been some improvement, I think, in industry engagement with collaborative research ventures. You know, I mean, obviously SciAps now and in the past, previous companies I've worked with have been really excited and energetic and invested in some of these projects that have yielded great benefit to industry and obviously to the companies in terms of sales and gaining credibility in the market space. But, you know, there's it takes a large investment. It takes dedicated staff to actually put the time in from both sides, you know, industry and the manufacturers of the technology, in order to get the best outcomes. So, yeah, I mean, that's certainly something that's near and dear to me. The company I'm working with now is a little bit fortunate in that our product release is quite new. I think some of these supply chain disruptions are down to single components or 2 or 3 critical components, which may not even be related to the analytical side of it. Maybe just basic things like screen controllers or whatever it may be that, you know, you can't get access to in the volumes that you need to supply the demand that's out there. So, yeah, that's my tea.
I loved it. I think this one's pretty special to you. You weren't as confident as some of the other people, but I mean, could you bring to the table that, as Juan Carlos Ordonez did, that you were originally an artist? I mean, you don't really look kind of like the theater type, but I think what you did by bringing this is just a tea that I think a lot of people, when they're listening to you, can relate with and also be impassioned and angry about. And I think that's kind of what we need, right? We need to not be as placid about some of these things. So I liked it. Well done.
Thanks.
So moving on then, after reading this paper that you suggested, which I liked very much, so thank you. I think many may be thinking, okay, now what are the advantages of using a PXRF, considering that LIBS can identify more than just the light elements? And according to the paper, it can detect all elements. It is especially sensitive to the light elements, which PXRF cannot detect.
Yeah, I mean, there are portable XRF that are out there and have been out there in the past that can detect elements lighter than magnesium reliably. Okay, so it's possible to do. It's just quite difficult, and you need to use either purge gases or, you know, now with the graphene detectors and things like that, we have improved sensitivities on some elements down in the lighter space. But certainly we can't do lithium, or you can't see hydrogen, or you can't see oxygen, and things that are, you know, that are really possible using the LIBS technique. Now, the paper that we put forward, this Harmon et al. Paper from 2019, you know, had a lot of different contributors and authors, and it was interesting, I think, and the reason I put it forward for this talk was that it was the first paper that specifically focused on LIBS for MinEx, but still gave a good overview of different types of LIBS techniques. And it does have some comparison to, or, you know, contextual information around how LIBS sort of fits into that ecosystem of that portable XRF occupies now, but in a minimal sense. But your point around, you know, the portable XRF, you know, they're quite different products. I mean, SciAps, the company I work with now, still makes XRFs. I mean, we didn't stop working in building XRFs for mining because we have a LIBS. They are quite different products. They are both handheld analytical tools. You know, they can do quantitative analysis and elemental analysis. Okay, both of them can. They They both have, broad element suites. LIBS, as you've said, has light element capabilities, but it also can do heavy elements. Okay, so the LIBS, it's a handheld atomic emission spectrometer. So it's a very, very different looking spectral data set to a portable XRF or an XRF data set, an EDXRF data set. But the spot size is also really relevant to the type of context in which you'd use one or the other. So light elements is one thing, but I think that the capabilities of the LIBS, whether it be in a handheld, a benchtop, or a standoff system such as used in core scanning systems, we really can use the spatial resolution of the LIBS to our advantage to understand elemental distribution within the sample, and to also be able to look at things, like the association, deportment of elements. Okay, so from a perspective of being able to say specifically in a very small, like a mineral bleb, like we saw like a little stringer of sulfide, we could actually get the laser and focus in just on that and understand what the chemistry is of that sulfide. What is the signal that we're searching for here? Is it a barren or a fertile sulfide that we're looking at here? And that, or whatever it may be, specific mineral. Whereas with an XRF, you can shoot it in the general direction, but you don't categorically know that all the copy you're seeing is sitting within that sulfide bleb if you're looking at something like an ultramafic, for example. So, it could be coming from some of the other minerals in the surrounding rock. And even with collimation on portable XRF, you lose a lot of the sensitivity that you require for getting good analysis. Certainly when you get down to smaller spot sizes, as you can do with a LIBS, then you're seeing the mineral chemistry in its concentrated form. It's not diluted down by several different phases. Okay, and that's really powerful. So the context of when you would use one or the other, it really depends on a range of things. The elemental suite you're chasing, certainly the sample presentation is really key. The LIBS is a semi-destructive technique. It's a not completely non-destructive as portable XRF is. Portable XRF, you could shoot through a bag. With LIBS, you could shoot through the bag, but you're going to analyze what the bag's made of. You're going to burn a hole in it. So, you're ablating the surface of the material, and you're analyzing very much a superficial measurement with a LIBS system. So you can use both of these products or analytical devices in concert. I think there's been some really successful case studies of using LIBS, for example, for lithium analysis, and where people are looking at lithium in a soil. With the soil, you can shoot an XRF, like I said, in a bag directly in situ if you wanted to. And with a LIBS, you actually need to reconstitute the soil with a handheld LIBS at least, and pelletize it back to a solid form to get a good analysis, really. So, the benefit of being able to do an element you can't do with portable XRF, lithium, probably justifies that effort. And certainly with companies like Reflex, Index Reflex, with their field prep equipment, we've had a lot of our clients that have been using it for superficial geochemistry utilize things like the Reflex press and other, lab presses that are field deployable to some extent in order to reconstitute these particulate samples. But in general, your LIBS is going to be a much better product to use, let's say, with the chips in RC drilling or the core in diamond drilling than the fines, unless that's something you're willing to do the work and do the prep. Whereas an XRF, it's more flexible for soil geochem, for RC drilling. Your XRF is gonna work well because of that sample presentation aspect, and the LIBS could yield you a lot more data, but would be more problematic with those particulate samples for a handheld LIBS. There are standoff LIBS that are available that would work in a standoff position with analyzing soils, but we don't deal with that at SciAps.
And I think you bring up a really good point there, and it's something that we try and push a lot here on this podcast, and that is to say that whenever you're planning any kind of survey, it's really important that you have a question. You're not just buying an XRF or PXRF or a LIBS because Rio Tinto has one and Rio Tinto thinks it's the best thing that was ever developed in the world. You're buying it because you have specific questions and you're evaluating the technologies that are available out there against each other based on what it is that you need to see in your data. Are you working with soils? Are you working with drill core, as you point out? Do you need, for whatever reason, to ensure that you lose none of the sample in what suite of elements, as you pointed out. So I think that these are all really, really important things that we need to keep in mind while we're planning our surveys and before we're buying and investing money into things that are expensive, the PXRF, the LIBS, any kind of system you're going to purchase or do a scanning survey for instance, they're all going to be expensive to a degree, but it won't be money wasted if it's helping you discover or it's helping you in MET or whatever it is that you need it for.
Yeah, and like I said, the use of multiple techniques, like if you were sending samples into a laboratory for an analytical suite, it's quite likely that you would be getting 2 or 3 different analytical techniques employed simultaneously on the same sample set. And so, for LIBS, you can take what's good and strong with a LIBS and then take the rest from the XRF, acknowledging that they are sampling, their sampling is different, that the technique is different, as they both have their own bias and their own challenges. But similarly, a LIBS could be employed on the samples, let's say in a pegmatite that's in a weathered environment and you've got cover. You may have existing portable XRF data that tells you a lot of information. You've done lithium indexes using your portable XRF, but then when you actually look at the samples with the LIBS, you may get some information in there with the lithium about mobility of lithium in that system, how that relates to your index in different parts of the weathering profile, how the fresh material below relates to the surficial expression of it in that environment, in that weathering environment. And these things, they're never a direct cookie cutter. You've got to tweak the models you're using and understand the techniques, what they're telling you, and take that on board in order to develop something which is really a localized exploration model that would employ that technology fully.
Such a great point. And so for those, just moving back just really quickly, for those that haven't read this paper yet, the Harmon et al. Paper, could you just give a brief overview of the paper and explain why you think that it's a really great read for people that are interested in using LIBS?
Yeah, like as I said, it's kind of like there's a first paper I could find, and that luckily I was involved with here, that really brought together a bunch of different case studies that talked about different types of LIBS products as well, not just our handheld from SciAps, but there was a range of other lab-based systems that were employed in some of the studies. But there's a range of case studies in there from several authors that talk about a really wide breadth of applications which potentially could be employed with for the benefit of mineral exploration. So there's been several papers in the past that have talked about analysis of geomaterials or just LIBS more generally, and this one was really kind of focused. And we brought together the group specifically with the intention for that. So, the conceptual studies that are in there have led to development of workflows, which now we're looking to push into product to allow people to use these things in a working environment. So I think that, it's information is very current and very pertinent to how potentially people will be experiencing the use of this technique in a working field environment. So, but this is foundational. The studies that are in here really set the proof of concept for us to push forward with the development of some of these ideas. And so that will be translated into product. And I think some of the concepts that are in this paper already are being realized in some of the manufacturers that are out there. The other important point, I guess, is that although we're talking in this paper, about these LIBS as products, because they're manufactured items that have come from manufacturers that build these things routinely, a lot of the other LIBS papers that are out there often are dealing with custom built systems. So more and more, obviously, as the manufacturer base grows and the installed base of product in the field increases, we're going to see more of these kind of things that you could relate directly to the product that you're going to use, or an analogous product. Then a lot of the earlier papers that I was working on in terms of trying to work out what we could do with this stuff were really, one-off custom-built things that were built in a lab by researchers. So, you could never translate that directly because the spectrometer array or the laser type that was used or whatever it may be had slight variations in the theme of what we can achieve with a specific setup.
It's a really interesting summary, and especially because I hadn't understood until we had been talking a little bit earlier that most of the papers out there for libs aren't necessarily these, case studies, because I think we're so used to just seeing a lot of case studies in the geological literature that I didn't realize that here in this piece of technology we're actually lacking in that. This paper that you suggested for us to read, and then there it was, all these different case studies, and it really just kind of brought to the forefront a lot of the power in it and how special it can be for these specific applications.
Yeah, I mean, the portable XRF space, today we take it for granted that there's all these papers you could look up if you owned a Niton XL3T or Gold, or if you owned Avanta, or if you owned, a range of different specific products, you could probably find a paper that's been written using data from one of those devices. You know what I mean? There's or a TerraSpec or a spectral evolution, system. There are a multitude of case studies which are dedicated to understanding how that particular unit worked in this particular setting. Whereas LIBS is quite a lot younger, I think, as an analytical technique in general. But certainly, like I said, in a commercially available sense, we're really in an early uptake phase at the moment. From an industry perspective, with the handheld LIBS in particular, and as I'm aware, most of the other LIBS systems, which are generally much bigger, lab-based or, I guess site-based type pieces of equipment, they're still finding their feet in industry with uptake and use. And so, and in a lot of those cases, people still have a lot of a vested interest in protecting their IP around their competitive advantage. So, this has been one thing, I think, with a lot of different technologies in their early uptake. Some people are getting a lot of benefit out of it that are investing a lot of time in it, and the ability to translate that out to the general industry can be stymied by those relationships and that confidentiality. Okay, but obviously you need to walk through these steps to be able to get the product to a point where it's accessible for a lot of people. Portable XRF, really, we saw its uptake, I'd say 10 years after we saw the first products, and we're sort of, now about at the 10-year mark with the handheld LIBS at least, and certainly the general availability of being able to buy a LIBS off the rack from a variety of manufacturers in a variety of settings. So I think, this is probably not going to replace portable XRF holus bolus, but it's certainly going to augment and fill gaps that portable XRF has. I think, the speed of acquisition in particular, and the multitude of data that you can generate with these things in the core scanning environment in particular is massively powerful, as you'd be aware from your past experience. Speed of acquisition and sampling, sample density resolution. These things are all, something that LIBS excels at. So add to that the breadth of the elemental suite that's capable, or the textural information within that highly textured spectral data set. There's a lot of yield that we're yet to see out of LIBS spectral data, and the information that we can generate from these things is incredibly rich and powerful. But the data set is complex.
For sure. So at this point, I want to talk about calibration, because I believe that as geochemists, we cannot do enough to stress the importance of it upon the wider geologic community. And so in saying this, I have some specific questions, but before I do, because I know you can see them, is there anything that you'd like to start out with saying?
Yeah, this is a really key point to the use of, a range of different techniques. As you'd be aware, using hyperspectral data, doing quantitative analysis for spectral data, using multivariate techniques is possible. Okay, totally doable. Really powerful for doing mineral identification and potentially quantification of compositions. It's a thing you can do, but it can be, it's not a straight line in a lot of cases. So things like portable XRF in particular, that a lot of people are trying to translate their ideas around the use of especially a handheld LIBS into that context of portable XRF in the past. Portable XRFs have far more dynamic and well-developed algorithms around the interpretation of the data for quantification. So when you're building calibrations, there's probably a few different levels that you need to come at it from if you're thinking about it from that point of view. So, with portable XRF, the factory often determines what the calibrations are for a lot of users. And certainly with LIBS, to go back to your original question, there's factory calibrations that we can issue. However, the calibrations that we build at the moment with SciAps in particular are using a univariate approach. Okay, so they tend to have a high degree of matrix specificity, and we would build a calibration that's specific to like a lithium pegmatite or a general soil or a sulfide. Okay, and we have specific components within that univariate input data that are specific to that type of matrix that we're going to test. Okay, so the users also with a LIBS and the software is available freely with the units can build their own calibrations if they've got their own standards. Okay, they can do a lot more than you can do with an XRF, but this is like an element by element standalone calibration. Okay, that becomes quite personalized to the type of material you're exposing it to. So there's a couple of questions that you drafted ahead of this that that talk about whether we're better off to have a multitude of elements, a bigger element suite. Even with a portable XRF, bigger element suites don't necessarily always yield better performance on the whole range of elements you're doing. You open up cans of worms. There's sweet spots in the spectral data that you can work with. Portable XRF or EDXRF data in general has a lot less features, and so does shortwave infrared. A lot less features. They're probably fatter and a little bit more, I guess, finessed in terms of where they sit. But with LIBS, it's like, it's like atomic emission is like OES data. It's just like heaps of lines, really, really short, sharp lines. If you can measure them, so it all comes down to, if you're calibrating, understanding which of those potential lines are not going to be interfered with in the matrix you're working with in order to choose those candidates when you're doing a univariate calibration. Now, with some elements, there's few interferences typically across a range of different material types, and you can get away with univariate, and univariate can yield better data. Okay. However, a lot of the literature, as you'd see in the paper with Harmon, historically uses more multivariate chemometric techniques. Okay, it's more dynamic, but still, as with hyperspectral data, you have to be restrained in terms of the size of the training sets you use. You have to understand where the scope is within the samples that you're working with in order to build those training sets effectively to get the best multivariate models. And certainly, there are LIBS products in the market that come with multivariate packages. We're currently working on several levels with development of code and development of the mechanics for this, development of the libraries. And that's something that's going to require groundwork to really make it available and, potentially parts of it open source. So, at the moment, as I said, there's a lot of this stuff that's locked up in specific work that's been done by companies that's confidential, commercial in confidence. So, the LIBS data and the calibrations of it less flexible because they're an empirical calibration, and they whereas a portable XRF, when you use one out of the box, there's a few different models. You could use Compton normalized models or fundamental parameters based models, but they are typically more flexible, but still have their own idiosyncrasies around where they're strong and where they're weak. And sometimes people use portable XRFs in the wrong context, using those things and yield poor data. So, it's the same sort of issues are addressed, and certainly it's possible with portable XRF to add elements empirically. It's possible to, to work on improvement of the factory calibrations with portable XRF. Several of the manufacturers allow quite a deep level of access to their calibrations to be able to shoot additional standards in, to be able to change the way you model certain data for certain regions of interest. And that's probably evolving a little bit. So I think that the portable XRF space is now, that there's a part of it which is developing those additional advanced skills, which will actually feed well into acceptance of what you'd need to do with a LIBS to get it really working well for the specific application. Yeah. So I'm not sure if that was a long answer to a short question.
I mean, honestly, you picked up on a lot of my different points here, and I think that you did a really good job of talking about the similarities and differences between the different types of handheld calibrations. And just in general, I mean, companies that I've seen don't calibrate their data because they don't know about it. They're not aware that this is something that they have to do. So I think it's really interesting that when you're getting your libs, because it is so specific, that I'm not going to say out of the box, but out of the box, it is calibrated towards your specific program that you have. And I think that's something that's really important for everybody out there that's listening to know, because maybe you did get it initially for a lithium pegmatite, but maybe perhaps you also have another project where you think it would work well. Well, now back to the drawing board, call up your rep, because you probably won't know how to do it yourself, but call up your rep and say, hey, we're moving over to something different now. We want to use it for, maybe this kind of like a sulfite application. What do we have to do to make sure that we get the analyzer calibrated? It really did do a good job of answering my question.
Yeah, depending on the configuration that was ordered, that's really, really relevant, Sam. Depending on the configuration that was ordered, it's quite likely that there's a whole heap of calibration shot information in the database that could be reutilized for a more specific application, or even just to augment like a client sample set that you've had assayed at a lab. You could actually pull into that calibration some of the certified materials that have been shot previously with some of our more general calibrations. So we, like I said, we build lithium specific calibrations, but we also have kind of like a generic, starting template, like a starter kit that comes on most of our instruments. I mean, the other thing I guess to consider with LIBS too is like a near infrared, shortwave infrared vis spectrometer. Okay, you've got the spectrometer arrays that you've got determine the data you catch. Okay, and the quality of that data, and what you can resolve in terms of features is determined by the types of detectors and spectrometers that you're using. So you have a spectral bandwidth, and with LIBS being, essentially like a simultaneous laser pulse and then collection of data at a time slice after that pulse is cooling, we catch whatever we can. So the wider your net is, the more information you get. And then the better resolution the different portions of that net are, the better we can discriminate between neighboring peaks and features within that data. So, I guess portable XRF probably is different in that it acquires data over a period of time, and then we actually modulate the energy output and collect data. So your actual residence time with the sample is usually longer, depending on the element suite you're chasing and the instrument you're using. You might be, dwelling on a sample for a minute or more, per shot. Whereas with LIBS, it's like a nanosecond pulse laser or less with some systems, and it catches everything it can at a very, very short time slice after that in the order of milliseconds. So, you take that opportunity, and so people using some instruments that we have, more cost-effective instrument offerings for people that do really specific things like just lithium. So that would only have one spectrometer. And we have some systems that have 3 spectrometers. And with some of the lab systems, you can dial up that capability around your spectral bandwidth and plug in new spectrometers as you need for the specific capability that you're chasing. So, sometimes you need to also consider, it's like using a portable XRF from 2005 and trying to compare the data directly to something bought in 2022. They're going to have different types of information that are being captured, and you might have a limited element suite. You might have things with that information that you can't cross-correlate to the new stuff, or your instrument that you've got may just not be capable of doing it. It's like saying I've got my old Niton XLT and I want to do magnesium analysis. Like, you're dreaming. There was no capability for that.
Oh my God. Just a little joke there, no big deal. So that said, because it is so specific, the calibration, do you also recommend setting up a QA/QC program similar to what you would do for a standard geochemistry and, dare I say, standard PXRF program?
Yeah, I mean, I think it's really important to understand, how well the calibration works for the materials you're working on. So I think with LIBS in particular, that a validation step is really important if you are building a calibration for starters, that you establish like a baseline of what your kind of expected performance is going to be on the type of samples you're going to be working on. I think that's key up front. But in terms of ongoing QA/QC, sometimes I think, with any of these things, especially if you're doing some sort of calibration adjustment, with portable XRF for testing through a bag or whatever it may be, it's more important to understand stability, So I think with the LIBS, certainly we have wavelength calibration factors built in. We have the ability to build in intensity drift correction standards as well, that are like samples that are from within our calibration curve, that we can use to adjust for drift that's occurred on the instrument over time. But in a routine fashion, it's really important to test the same samples routinely at intervals. In particular with portable LIBS, maintaining the optical pathway is critical. So if you, and because it is a destructive technique where it's firing and ablating, it's tiny little craters with a handheld unit, we're talking about maybe up to 50 to 100 microns depth and maximum, and more typically 10 to 20, let's say. And then the diameter of the crater, we have a 50 micron laser, but it probably generates like a 70 to 90 micron crater with an ejector as well, and some damage in a circumference around that. Depending on the mineral, we can get breakage along cleavage. So, when we're testing like that, there is dust, and although we use an argon purge that can help maintain pressure in the chamber where we're collecting the optical signal through, it's possible to get dust buildup in there. And if that happens and you see a decrease in the responses from the QA/QC samples, then it's time to clean the device. And so maintaining that and ensuring that you don't continue to do a heap of work with a diminished optical pathway and therefore diminished signal is really important, especially, if we're interpreting the data quantitatively. Typically with our univariate approach, we use a relative intensity ratioing. So we want to make sure that all of the data the raw spectral data has similar intensities coming through at us for the different wavelengths that we're pulling the data from as well, for the numerator and denominator in the intensity ratios.
And you mentioned instrument drift. Do you find that, so for instance, if you're using a handheld, Teraspec or something, so that would be for hyperspectral data. So then that, the recommendation is every 15-ish minutes or so, just recalibrate. And then whether it's working with the spectral data on the battery or the PX drive data on the battery, if the battery life's 3 hours, 2.5 hours in, you probably should switch it out. That always will cause instrument drift. Is there anything more that we should be aware of when using a handheld LIBS device that you will definitely get drift? Is it temperature dependent, for instance?
Yeah, it is temperature dependent, but the internal thermal dynamics of a LIBS system are quite different to something like a portable XRF in particular, or to systems that use electrocooled detectors like N-gas detectors, which might have some sort of TE cooling on them. So the thermoelectric cooling. So in terms of the temperature drift with our LIBS spectrometers, when we turn them on, they force you to do a wavelength calibration. Okay, so that uses an internal standard of 316 stainless steel. If we have 3 spectrometers, it drags all the regions and peaks into the location where they should be. And that's it. Then you're good to go. So what we do have built into it is, you have a constant monitor of internal temperature as well. I think the instruments have the ability, if you're working in a colder environment, to actually pump the laser to the point where the laser heats the internal instrument up to a temperature that's within an acceptable range, and we color code it. So it'll go from being blue to being green to being orange to being red, but the thing we don't have, like a portable XRF, is a tens of thousands of volt X-ray tube humming away right next to a Peltier cooled detector, which is kind of a mismatch of bedfellows. So what we get with the LIBS is probably a lot less of that internal heating and probably more of an ambient temperature input. The instrument's internal temperature from the laser pumping, especially if we're running high rep rate stuff, doing element mapping, stuff like that, sometimes you do heat the laser more, and we want the laser to pump efficiently. That's the main thing. But we have excellent thermal management built into the instrument. They're ribbed aluminium housings, or heat sunk through, but they don't generate anywhere near the level of internal heat that an X-ray tube does. And then the detectors that we use are essentially like a CCD array, so they're not as sensitive. I think the main issue you would have is flexion and things like that on the spectrometer mounts. And so what we see is, if you get the instrument up to a temperature, that is in the green zone and you operate it at that temperature, then it will be fine. The instrument will actually prompt you to do another wavelength calibration at internal temperature variations. So we have a set, and it's impossible for the instrument to continue testing when it hits that temperature variation from when it was previously calibrated. So it forces you to keep it stable.
Last question with kind of QA, QC and calibration. Is there any issue generally with wet samples, or does it matter if they're dry or wet?
Yeah, I mean, there's a few things here. So you've got, pore moisture and surface moisture. So let's just say you're out in the field and it was raining and you were trying to sample a piece of outcrop. That's one thing. Even if you were drilling and, because of the drilling fluids, you've got surface water sitting on the chips. That's different to if you have like a saturated sample, okay? The LIBS will see and actually be able to analyze a large proportion, well, virtually everything in the sample. I mean, like an XRF will see that light stuff, which is, hydrogen and oxygen as light stuff. A LIBS will say there is hydrogen and there is oxygen, so it will actually see that. And if you're looking at samples, which you probably are, that contain especially oxygen, and you're using, let's say, oxygen, which is common with our broader range spectrometers as a normalizing element in our algorithms, then the water can have an impact on that, So I guess if the sample is saturated, like a mud or something like that, that is definitely an issue that you'll have difficulty with our LIBS analyzers, at least, getting a good interface, not getting contamination on the instrument. So there's several levels there. But if the sample was just wet or it had been washed, if you could dry the surface, even wiping it off with your hand, what the handheld devices that we offer do is they generally clean the surface before they analyze it, because if there's any dust or whatever. So you can shoot the laser with non-analytical shots. So if you're always working in samples that like drill chips or whatever that had moisture in them and you wanted to, you could actually increase the cleaning shots, as we call them, and they're essentially acting as drying shots in that case, and they would vaporize the water before you start collecting analytical data. So you can customize the routine. But again, this gets down to another level of finesse. Like our factory offering would have a couple of non-analytical shots prior to us collecting data. But you can, and for certain applications where we're testing alloy materials that are covered in potentially corrosion or paint flecks or whatever it may be, and we're trying to get the actual substrate material properly, we may do 100 cleaning shots, and fry the surface. And then we go, okay, let's take the data now that we've got a clean surface. So, yeah, they're kind of cool like that.
Yeah, definitely cool. Can you explain to us the difference between qualitative and quantitative LIBS applications? And in terms of, more of a field-based geochemistry utilizations, what do you think would be better for us?
Okay. So, I mean, the qualitative application of LIBS is pretty well established. I mean, like I said, even with mineral identification, there's a huge amount of research that's being carried out into mineral IDs and mineral fingerprinting, geochemical fingerprinting using LIBS. As I said before, if you have a broadband LIBS that collects a wide range of bandwidth, then you can typically get a very comprehensive fingerprint, which will, discriminate very fine differences between different parts of end members within a series. And the qualitative applications in a greenfield environment are probably better, in my view, as long as the geologists using it understand the context of the information. They take, at the moment, the software that we have on the handheld isn't quite there to be able to feed you information based on that qualitative data to an extent. We have an analytical mode called Element Pro that will tell you the mix of different elements that it identifies in the spectral data. You can actually look at the spectral data, qualify that, making sure it's not interferences. And people have used these, I guess, indexed values effectively for things like mineral chemistry vectoring, but the people using it have developed conceptual models around variations in the element mixes, in specific mineral phases. So, it's not just an out-of-box solution unless you're actually, aware of the implications of those changes in that information that you're receiving. So, the qualitative applications, I think, are very, very powerful, yet in the handheld environment, at least, we are still developing some of the software tools to develop a user interface which fully encapsulates the potential of that. We have some aspect of it now, and you can definitely use it, and you could use it with a guide to a fairly, basic level geoscientist. But you need to develop it first, and it's fairly case specific. Whereas the quantitative aspects of it, you generally want to be aware of what you're shooting before you employ an empirical calibration to get reliable data. So it's, we can use this in a two-step fashion as well, where you can do a qualitative first pass, get a feel for what you're looking at. Say, okay, I believe that white mineral is spodumene, and then you can shoot it with your lithium spodumene calibration, and it will give you a quantitative value of that mineral's composition. So that's kind of the workflow, but streamlining that workflow, making it more dynamic, where the instrument could actually identify what the material is first and yield the right quantitative value and potentially a mineral ID at the same time. That's the golden chalice at the end. That's the holy grail, I
mean, back when I was working in my master's and doing EMPA, microprobe data and SCM data, they couldn't even do that. I had to tell them what it was. So, you guys are still chasing, I think, what I couldn't get back in the day. So,
and I mean, the spot size really, being able to actually get within a specific mineral phase, or even within zonation within a specific mineral, that's where these microanalytical techniques yield a lot of benefit. And going back to the portable XRF LIBS kind of context, which one's best where, the portable XRF just doesn't have that, unfortunately. Collimated XRF, the things like the Tornado micro XRF systems, they're getting into that space. They've got their spatial resolution now, and I think that there's a lot in this space going on that all sort of is going towards having this information and that textural information as well, alongside the rapidity of collection is another thing. Some of these bigger lab systems, the speed of delivery of data, the cost of delivery of data is very high. So developing these new analytical methods and techniques is key to getting broad scale use of these ideas, which have been very well developed in the spaces you were talking about, and in laser ablation as well. So there's a lot of interesting models that have been shown to be effective exploration tools that now we're looking to see how much of that can we take and project into field or in situ environments and generate data rapidly and cheaply that's reliable.
Pivoting a little bit from more of this the field stuff, one thing that I became very interested in over the past few years is geomet. And in this paper, there was an extensive section devoted to grain size proxies using the LIBS. And so the idea behind it, according to the paper, is that successful grain liberation is vitally important in extraction by techniques such as gravity separation, flotation, leaching, and magnetic and electrical separation. Also, that this dictates overall recovery. So now this paper was written in 2019. And at the time of writing, it showed that while grain size was underestimated by about 50% as compared to MLA or ChemScan, LIBS can be used to rank samples by grain size, and it was successful in detecting and measuring combined copper sulfide grains. The question here is, has there been any update in the world of LIBS applications to geomet? I know this is a very specific one for grain size, but just curious, what's been going on?
I'll give you my 5 cents on this, but I would refer you to potentially another one of my co-authors, Cassidy, who you know well, Cassidy Harradine, and she was actually the contributor that put this piece of work together, and I believe it predates significantly the paper. She has subsequently just joined MDRU as a postdoc and is working on some of the stuff related to the LIBS for mineral chemistry vectoring and data management and the stuff that I've just been talking about. So she she would be able to expand a lot more on this and where it's gone. But I did touch base with her, and she informed me there hasn't been a heap going in this area. But also to qualify, you, as you said, you've gone away from the handheld space. One of the big things with grain size, it's relevant in the handheld space as well, that if we're doing microanalytical mapping, and in the paper that we put forward, there was an attempt, and it's possible, to stitch together multiple data captures. We could do it potentially if we were mounted as a sensor head onto a core scanning system, for example. But you need coverage. You need the population of data. And in terms of LIBS spot sizes, typically we're working in the, let's say, 50 to 200. The Mars systems might be 400 micron spot sizes. So you're in fairly coarse sort of territory to start off with. It's possible to do this, and certainly the data analysis that was presented in that part of the paper suggests some reasonably good outcomes. One of the issues that we face with the handheld, with a fairly small field of view in a single capture, is actually generating enough clean data, like where we're sure that we're in a specific mineral and it's pure. And whether that means we're looking at a sawn rock slab, piece of drill core, or a mineral mount, that we want to make sure we're getting just the epidote signal and not the epoxy, is this kind of collection of mixed spectra boundary data, so that the data that she's presented there and other stuff that's in this paper and I've seen elsewhere relates, either to fairly coarse-grained materials, or in this case, where you've been able to model that data because you've acquired, I think the minimum data set that yielded anything that was really beneficial was around about 650 data points. You know what I mean? So, and I think that the data looked like it improved significantly beyond when you got to about 1,500 to 2,000, and that was over a couple of square centimeters. So, that's a fairly high resolution data set. It's kind of a larger population. Certainly, I think some of the standoff libs that, can acquire data at 1,000 hertz, you can generate a lot of information very quickly with these. They can do things like this, certainly, as well as things like elemental distribution from a, if you're looking at gold, for example, gold distribution within drill core or within a rock slab, very quickly, very effectively. And you can either do it looking at the gold compositions. This is another thing that LIBS is able to do, is say, okay, you've got gold in this, projecting this as a surface analysis here, here, and here, and here. But in this sample, you've got two types of gold. One has this alloying characteristic, one has this alloying characteristic. They are different types of gold. They've come from different, events or pulses in the system. And, that helps you understand things, but also the distribution and the association of those different gold types are very clearly mapped out in that high resolution data set. So, yeah, I haven't seen a heap more done on this from a geomet perspective, beyond maybe some work that talks more about that elemental deportment, and certainly around some of the gold applications for gold alloying.
Very neat. I'll definitely follow up with Cass on this.
Yeah, for sure.
Definitely.
He said to say hi.
Hi, Cass. So the summary section of Harmon et al., it paints LIBS in a very favorable light. And I would argue also that our conversation thus far has been fairly favorable, I would say. What beyond what we've talked about do you see as opportunities for the technology in the mining exploration industry?
Well, as you can tell, Sam, I'm a believer, but I'm also trying to put forward that it's not a walk in the park. It's not trivial. The reward is very great.
This has come across, which I think is so important, because just to interrupt you here, even something as, quote, simple as PXRF is very abused. It's really sad how poor these data sets are being collected. And I really appreciate your optimism of this technology, but also the stress that you've put on that this requires more than just powering it up. Like, this requires a lot of thought, and this requires users that understand what's happening and all the different caveats that's going on. So, said my piece. Continue. That's my little bit of
100%. The reward is great, and personally, I think the as I said, the holy grail, the end point for this, and some, like I said, there is data packages, data analysis packages out there for LIBS products that are able to do multivariate work. They're able to do mineral IDs. They're able to do all this sort of stuff. You know, the one thing that a lot of other analytical techniques have when it comes to potentially mineral ID is quite a lot of blind spots. LIBS doesn't seem to have that if you collect a broad enough, high resolution enough data set. We seem to be able to have enough elemental information and enough matrix-based pattern, you know, textural information within these spectral data sets to yield most, if not all, minerals. That's a big call, but I think that that's really the end goal with this is you know, being able to do mineral IDs and quantitative mineral chemistry simultaneously at high spatial resolutions in large data sets or in focused pinpoint where you say, what's that, you know, white mineral, what's that black mineral? LIBS can do that. You see a black mineral and you're drilling in a, you know, copper environment, you shoot it, it's got boron in it, you go, oh, maybe it's boron, you know, maybe it's tourmaline. I don't know, you know, these sorts of things you don't have with other techniques. They've got holes either from the analytical application for one of the techniques, another one might be able to do it, but not a whole heap of the other stuff you want to do. So the idea that we could, on something like a sawn drill core or even a hole drill core, run a track very quickly, get quantitative information. You know, one of the steps in the workflow to process these data in multivariate, from my experience, is a pre-classification of the spectra. You know, like one thing we do with our alloy testing, alloys are very neatly compartmentalized into a bunch of different groups. Okay. So if we run like a PCA analysis over, and you'd see that in some of the papers, case studies, PCA, you know, different types of partial least squares regression, these types of things are able to have a bit more grunt than what we do with SciAps for our alloy classification, that we do a pre-classification and say, okay, well, this looks like a brass, or this, you know, a copper-based alloy. So we'll employ this curve set, which has these elements that are really relevant to that application, and it automatically on the fly makes that call for you. You know, you shoot the sample, it looks at the spectrum, it says, I think that's this. It goes bam into its little calibration library, and it says very neatly, that's this, that's the right calibration curve for it. There's your data, there's your alloy match grade, bam, bingo. You don't get that in geochemical environments. Generally speaking, you've got a whole heap of gray areas and a whole heap of mixed up stuff, you know, and it's not that simple. So when we employ these more powerful techniques, first of all, to, as I say, segment or pre-classify the data out into different types of matrix types, okay, or even spatially, like I said before, we can say, yes, this is a clean example of an epidote spectrum. It's not mixed with the neighboring mineral phase, okay? So we can say, okay, already we've just identified within this area, these are all epidotes and they're clean. Now we can we understand that that is this type of chemistry. It's this basic type of matrix, okay? And it'll apply the right calibration curve. But on the way there, we already really are picking up the mineral ID. You know what I mean? It's like a necessary evil to get to good quantification is understanding what the matrix is. What is the chemical makeup of that sample and which calibration set would be most suitable for it, either by a univariate method or in that case, you know, we can have multivariate subsets, which are based on training data for a bunch of sulfides, a bunch of carbonates, a bunch of aluminosilicates, this type of thing. But we make that pre-classification, then we can have scope on the different parts of the data set that we're working with, and then we can employ the correct or more correct, most correct analytical approach to processing those spectral data quantitatively, and then, you know, we've got a higher certainty that our quantitative information is actually accurate.
And is it necessary to say, before you start collecting spectra, is it necessary to say, hey, we're going to be looking at, not necessarily, you're not like talking to it, right? Like you're not saying, hey, LIBS, this is what we're going to do today, but more or less, you know, setting it up for success, that we are in an environment that contains epidotes, carbonates, etc., and that these are about what you're going to see, so that, you know, at the same time, then all of a sudden you start to pick up that you have lots of tourmalines, you have lots of I don't know, what's something that's completely different? I can't even think right now. And lots of feldspars or something like that. Like, is it LIBS at any point? Is it going to get confused that you didn't set it up correctly, or can you calibrate after the fact?
I think, it's important at this stage that you absolutely determine what you're looking at before you do it. When we set this approach up, and as I said, already there are software packages that can do things like this. And it's just employing it into the handheld. So building the UX on, the user experience out to a point where it delivers this kind of information. There's a lot of, mechanics in the background that go towards that. I think the initial intention of this, the scope of this, is really to set the instrument up to identify the unknown. You know what I mean? To have a broad net. It will segment these data out no matter what it is. Okay. And I think it would, at the moment you could make a determination ahead of time with our instrument and employ the correct calibration curve that you'd already built on the instrument. Okay. That's totally doable today. But the building of the calibration curve for that material type, that's something that falls into the user realm. And certainly you would have to predetermine that you're looking at a sulfide. You're looking at, like an aluminosilicate. But certainly with feldspars, you could test an albite thinking it's quartz, and it's going to tell you it's got a ton of sodium in it. And so, that's like a really basic kind of binary test of an example of, 50 shades of white. LIBS is very good at that,
I love that. To round out, I think, our discussion, my last question is just, so far that you're allowed to say, and maybe just in a little bit broader terms, give us a little bit maybe more tea here, but what's been your favorite application of the technology? Either it could be the most novel or consistently reliable. What is it?
Well, I've kind of divided this into two sections. One is the most reliable and one is the most novel. So I think my favorite application here is definitely the element mapping stuff, and the things that we've just been talking about, because I think that's the real goal of this technology, is being able to utilize the spectral data to the maximum capability. It's optimizing the outcomes from this incredibly rich data set. However, the most reliable application, I would have to say, that's been successful for us, and certainly the first foray really into industry and beyond research, has been lithium. We've been in the fortunate position in the middle of a lithium boom to have the only handheld analyzer that can analyze lithium. So, it's that's been the real moneymaker up till now.
Well, thanks a lot for stopping by the show. And thank you, everybody, for listening to Geochemistry. And Andrew, thanks for dishing actually some pretty good gossip there, some good tea. And I mean, I feel more educated, and I hope that everybody else listening feels more educated on the LIBS technology, both where it is now and where it's going to be going in the future. I want to thank our sponsor, LKI Consulting, and to It's Water and Coma Media for our music. And if you want to learn more about the show or submit a request to be on the show or recommend a geochemist for me to chase up, please go to our website at geochemistry.com. I look forward to chatting with you all next month, and see you then. And in the meantime, thanks, Andrew.
Thank you, Sam. And thanks to everyone for listening, if you do.